Okay, it's my pleasure to introduce Teddy Einstein from Swarthmore College. He's going to talk about relative cubulation of small cancellation quotients.
All right. Thanks for the invitation to speak here. Here. So today I'm going to talk about relative cubulation of small cancellation quotients. I should mention that this is in part joint work with Daniel Gross and in part joint work with Thomas Eng, who's at the Technion. So just to give you a broad outline of what I'm going to talk about today is relatively, so at the beginning I'll tell you about what relatively geometric actions are. So the idea here, the relative cubulation means that we're going to try to construct these so-called relatively geometric actions on cat-zero cube complexes. I'll talk a little bit about the background. Then I'll tell you about sort of the main results about, surprise, small cancellation quotients of free products. And then lastly, I'll talk about sort of some of the techniques for construction. So I'm going to tell you about these actions, but you might want to know a little bit about how you would actually go about constructing one of these things. So if you feel like you want to interrupt me at any point, please feel free. I'm going to try to sort of gloss over certain definitions, and if you want to stop me and make me clarify them, that's fine. All right, so what is a relatively geometric action? So the point being that a relative cubulation is going to be you take a group and you want it to act on some cube complex nicely. So definition, let's let GP be a relatively hyperbolic pair. So if you don't know what that is, I'm going to cruise by it and then we'll circle back to that a little bit later to see how that's exactly relevant. And let G act by isometries. Recent journal reviewers say that I should say combinatorially by isometries. That's another story. So we're going to have this group and we want it to act on a cat-zero cube complex. And we're going to add the following restrictions. One, that we want this action to be cocompact. Two, every one of these, so P is going to be some collection of subgroups, and we're going to want each of them to act elliptically. So what that means is each one of them has to stabilize, be the stabilizer of some point, or really some cell. And lastly, every infinite vertex stabilizer is conjugate to a finite index subgroup of some P and P. So what that means is that if you have, your group is acting, and normally we think about proper and cocompact actions where the group is acting and the stabilizers are either finite or trivial, and we have a cocompact action. Here we're going to allow stabilizers to be uglier, but sort of in a controlled way that works nicely with the geometry of the group. So let me give you some kind of really basic examples of this that you might be familiar with. So here's one simple example. One, if I take a group and I take the entire group, this is relatively hyperbolic and acts trivially on a point. And I just realized I screwed up so we should circle back because I didn't tell you what the payoff of the definition was, which is that then the group G acts relatively geometrically on X twiddle, and we're going to call this cat zero cube complex X twiddle. And we also say G is relatively cubulated. So I'll sort of use these terms interchangeably. All right, so to go back to the simple example, the really stupid example is this group. It has a trivial relative hyperbolic structure by just taking the entire group, and then it acts on this point, and this is a relatively geometric action. So this is really stupid, but we'll see that it actually does something surprisingly cool for us in a minute. So hold on to that. And the other sort of example that probably most of you have some familiarity with is that if I take a free product of, say, two groups, this acts on a Bass-Serre tree. And is relatively hyperbolic relative to the collection of the vertex stabilizers of the Bass-Serre tree. So in particular, the two things you're taking the free product, the action on the Bass-Serre tree is relatively geometric. So in general, in some sense, you should kind of think of like what is something that's relatively hyperbolic. One way to think about relatively hyperbolic groups are things that act on graphs so that there are kind of trivial edge stabilizers, and then there are these peripheral groups that can possibly be vertex stabilizers. And then in addition, you want your graph to be hyperbolic, and these peripherals have to follow some rules. But basically, this is in some sense very closely related to being relatively hyperbolic, and there's a natural link between sort of the relatively hyperbolic geometry and this relatively geometric action that I'll make explicit in a couple minutes. So let me give you some kind of history as to how we got here and why relatively geometric actions. So if you've been paying attention to geometric group theory, the sort of big work that emerged was Hegel's proof of virtual Hawken, used geometric actions of hyperbolic groups on cat zero cube complexes. So in particular, one of the big theorems that he proved is that the following, that if G is hyperbolic and G acts on X twiddle cat zero cube complex properly and cocompactly, then G is virtually special. Oh, bye-bye. Okay, so if you know what virtually special is, great. If not, I'll tell you what it does for you, which is probably more relevant, which is that that means that G is residually finite, which I'll tell you what that means as well. In particular, due to work of Hagelin and Wise, it also tells you that G is so-called Q-surf, meaning that it's quasi-convex subgroups. are separable. Okay, so, all right, I just blazed through a huge amount of terminology. So let's sort of back up and say a little bit about like what this is and why you should care about it. So definition, let's let H be a subgroup of G. H is going to be separable if for all group elements that don't happen to sit inside H, there exists some quotient. So we'll draw it like this. This is a finite quotient with H contained in the kernel of the quotient. And B of G is not equal to 1. So the point being, now you have this finite quotient. Here's H, and you have a group element outside of H. There's a finite quotient that kills all of H, but doesn't necessarily kill this group element. So somehow there's a quotient where you can study this group element relative to H, and you can do that for all the group elements that don't sit inside H. And so this is this kind of thing is a big deal, because one thing we would like to do is to be able to study groups by their finite quotients. In particular, there's a very special case of separability. So G is so-called this residually finite if the trivial subgroup is separable. So in other words, what that says is that there's some finite quotient given any group element. And if I take a quotient, there's some quotient so that this group element survives in the finite quotient. And so in some sense that like your group can be studied fully through its finite quotients. Now, it turns out that there are examples of groups that are not residually finite, but it's still relatively little is known about residually finite groups, or at least which groups are residually, I should say it's relatively little is known about which groups are residually finite. So for example, if you were able to tell me tomorrow whether all hyperbolic groups are residually finite or not, you would be getting a very nice publication and a very nice job and a very big grant. I should also mention that this sort of separability has some really neat natural consequences. In particular, there's sort of classical work due to Scott about promoting immersions to embeddings. So imagine you have some map like this, where this is an immersion. And you might want to be able to sort of promote this to an embedding in a finite cover. Separability can do stuff like that for you. So this is a very desirable property, and somehow this sort of Q-surf property and having this virtual specialness was one of the things that was instrumental in cracking the virtual Hawking conjecture. So one natural consequence of all of this, so sort of theorem, in part due to sort of Groves Manning, who deserved the credit for doing a lot of the heavy lifting, and also myself. Sorry. Is the following theorem, which is if GP is has all P and P residually finite, so that's a fairly mild assumption to have these peripheral subgroups be residually finite, and G acts relatively geometrically on a cat0 cube complex, every full relatively quasi-convex subgroup is separable. So what this says is that you can basically do the same kind of thing when you have a relatively geometric action. If you have these, you have to add this sort of notion of full in addition to quasi-convex, and relatively quasi-convex is a little bit more complicated than quasi-convex. But sort of the right things happen when you have a relatively geometric action, and you can kind of extend this machinery from the hyperbolic setting to this relatively hyperbolic setting. I should mention that there's been some sort of other work in this direction. There's been work particularly by Hruska-Wise and Shu-Wise and others to sort of build other types of actions of relatively hyperbolic groups on cat-zero cube complexes. In particular, like you might ask, well, why not study proper and co-compact actions? And the answer is that they have been studied, but oftentimes actually coming up with an action that is proper and co-compact of a relatively hyperbolic group on a cat-zero cube complex is generally more challenging than in the hyperbolic case. There have also been sort of efforts to think about co-sparse actions, which are actions that they might be proper, but not necessarily co-compact. In our case, the part of the motivation for thinking about actions that are relatively geometric, that are not proper, but are co-compact, are, you could have things like have your peripherals be non-virtually abelian nilpotent groups and take a free product of them, then that will be relatively cubulable. But nilpotent groups that are not virtually abelian can't act properly on cat-zero cube complexes. So there is sort of a wider set of groups that are allowed to be relatively geometrically cubulated. The other thing, so I should note that there are efforts to study proper co-compact actions, sparse actions. So if you're interested, you should look up papers of Hruska and Wise, Shu and Wise, and also Oregon Reyes, who's a student at Nagel. All right, so I guess now I threw a bunch of definitions at you, so we might ask, what are all these definitions actually good for? So let's talk about some of the main results besides just the fact that you have this nice separability. So theorem 1 is due to myself and Thomas Eng. Let's let G be A star B. And now we're going to take a quotient by some relator set where R satisfies the classical C'(1,6) condition. And suppose that A, PA, and B, comma, PB are relatively cubulable. Then G is also going to be relatively cubulable. So start with two groups, have relatively geometric actions on some cat-zero cube complexes. Now pick some crazy relations, but not too crazy. So if you know the C'(1,6) condition, it's what you think it is. If you don't, the idea is you pick your relators and you don't want any two relators to have a lot of overlap, or at least the relators and their conjugates. You want them to have sort of less than 1/6 of their lengths in common. If you're interested in this kind of thing, you should look at the book by Linden and Schupp, which is a classic. Anyway, you can take these sort of fairly uncontrolled quotients other than the C'(1,6) condition and then magically get this relative cubulation result. So I should mention that this builds on a result of Alexandre Martin and Marcus Steenbock, who did sort of a similar thing, except in the situation where you have two groups acting properly and co-compactly on cat-zero cube complexes. I think they're hyperbolic groups, and then you take some No, they don't need to be hyperbolic, but you take some free product and then you take a relation, and they follow, and they have the C'(1,6) condition on the relators. So here's kind of a neat consequence that in some sense justifies, or at least I think in some sense justifies, relatively geometric actions as being a particularly useful tool for getting cubical machinery to work for groups that are not obviously cubical. So let's let G be a free product of groups, so that with A and B residually finite, and R is also going to satisfy C'(1,6) again, then G is residually finite. So what I want you to notice that's really neat about this particular situation is that in this statement, these groups A and B, there's no requirement that these be cubical in any way. So unlike the previous statement where I said start with relatively cubulable groups, A and B need not be relatively cubulable. You just say that they're residually finite, but somehow by putting them together and taking this relation, you can build some interesting action on a cat-zero cube complex that will show you that things are residually finite using the relatively geometric machinery that I talked about a couple minutes ago. So this is pretty neat. And in particular, you can see how this follows from the first theorem. So you start with this theorem and use the trivial cubulations. A and B act relatively geometrically on a point. And so by applying this theorem to those relatively geometric cubulations, you construct a relatively geometric cubulation for this group here. And then you see via relatively geometric machinery that it's residually finite. So that's kind of a advertisement for why relatively geometric actions might be useful for doing things in the future, is that you can kind of get groups that might not themselves act on cat-zero cube complexes, but if you can cook them the right way and get them sort of as peripherals in a relatively hyperbolic structure, then maybe you can avoid these problems and still use cubical machinery to prove nice things. So as I said, there's a treatment of this, a proper and co-compact version of this statement that was originally due to Martin and Steenbock, and some of the techniques that we use build on that. There's also another later treatment that was done by Cancellation and Donnie Weiss. So one thing you might ask is, okay, so I claim to you that these relatively geometric actions exist, but you might want to know how am I actually supposed to construct such an action? So here's how you do it. So I think this is in the first paper that Daniel and I published together, which is that, okay, so let's take a relatively hyperbolic group. And let's suppose that for every pair of points, x and y, in what I'll call DPG, this is the Bowditch boundary. I'll say more about what that is in a minute if you don't know what it is. There exist full relatively quasi-convex subgroups exists a full relatively quasi-convex subgroup H and in G, so that if I take the limit set out by H, has X and Y in H dash distinct components. Okay, so what you should think the picture is here is, imagine that here's my space, or here's my group in some sense. And what I want to be able to do is if I take 2 points in this mysterious Bowditch boundary, I ideally want to find some kind of full relatively quasi-convex subgroup that's also going to cut up my boundary into 2 pieces so that X and Y are on different sides of it. And this H distinct, what that means is that you don't want H to be able to take one component. You don't want H to be able to flip the components, which is usually not a problem because you can usually pass to some kind of finite index subgroup to avoid this issue. So that's sort of less of a big deal. But this is sort of a fundamental idea in cubical thinking, is to sort of look for these so-called codimension 1 subgroups that sort of give you a natural way to say, well, this is a half space, this is a wall, and on either side of this wall you have half spaces, and somehow that tells you how to build a cubical structure. So this idea is not new. So this all kind of grows out of results by Sagiv, construction for cubulation, and also the boundary criterion due to Bergeron and Weiss. So they have a similar statement for hyperbolic groups with the standard visual boundary. And so sort of if you kind of follow what they do with the situation for a relatively hyperbolic group, this is what you get. And that's kind of another reason why relatively geometric actions are kind of a natural thing to think about, because you can construct them using some sort of boundary criterion. Unfortunately, if you've ever thought about boundaries of groups, in particular hyperbolic groups, so hyperbolic groups have nice boundaries. Relatively hyperbolic groups are require a little bit more care. So I guess we should say, what is the Bowditch boundary here? So what you want to think about is the following. So we have, say, G, P, acts relatively geometrically on X twiddle, some cat 0 cube complex. Okay, so one thing that witnesses the relative hyperbolicity, so this is one way to think about relatively hyperbolic groups if you haven't thought about them at all before, is say I give you this group G and I have some collection of subgroups. And what I'm going to do is I'm going to take the Cayley graph, so draw your Cayley graph of your group, and now take some, so maybe I should draw some pictures. So say I have G here, and then I have a bunch of points P, P, these are all in P, all in some P and P. And now what I'm going to do is I'm going to draw a point up here. I'm going to cone off P. So what you can imagine you're going to do is you're going to take each of these peripheral subgroups and their conjugates, and you're going to cone them off. And effectively, at least if you think like a geometric group theorist, you're thinking coarsely. So what that's really doing is effectively squishing that subgroup down to a point, at least coarsely. You're basically making all the points distance 2 from each other. And what you want is for this resulting coned off Cayley graph to be hyperbolic And then you need to have some other technical condition called bounded coset penetration, basically meaning that like you don't want any of your peripheral subgroups or their conjugates to have too much overlap. They should sort of intersect. Whenever they intersect, they should intersect in some finite subgroup. And you don't want them to sort of stay near each other in the Cayley graph for a very long time. If you're interested in that, I think that it's sort of the term bounded coset penetration is originally due to Farb, and it's in his paper on relatively hyperbolic groups. Okay, so the point of this is that, okay, so by a theorem of Charney and Crisp, the coned-off Cayley graph and this X twiddle, these are actually turn out to be quasi-isometric. So the idea being that, like, you know, what the real result that's in this Charney and Crisp 2007 paper is basically a relatively hyperbolic version of the Milnor-Schwarz lemma. And so, like, you know, if your stabilizers satisfy the right properties, then you're going to get a quasi-isometry. In particular, this says that X twiddle, the one skeleton, is a delta hyperbolic graph. So because this coned-off Cayley graph for a relatively hyperbolic group is hyperbolic, and hyperbolic passes through quasi-isometries, you get hyperbolicity for the one skeleton of this relatively geometric action, or both the cat zero cube complexes that you're acting on. Another thing that's nice to note is that you know, vertices, I should say, cells in X twiddle with stabilizer should say commensurable to P to the G form a connected and compact graph. So you can basically take, like, you know, say I have all the cells that are stabilized by a particular peripheral subgroup, and they sort of live in some finite universe. And so what you can do, in fact, you can collapse finite stabilized subgraphs to get a new graph with trivial edge stabilizers. So basically you take, like, okay, so here's these vertices that are stabilized by P, and I just squash them to a single vertex, and then you're happy. Because now you have trivial edge stabilizers, and each P to the G is going to stabilize exactly one vertex. Okay, so I promised you that I was going to construct the Bowditch boundary. So as a set, so let's call this graph gamma. The Bowditch boundary as a set is going to be the boundary of this graph. So imagine you take all the possible direction rays out to infinity with the usual equivalence relation. But unfortunately, that's not quite enough. You need to take the vertices stabilized by a peripheral conjugate. So somehow you need to have parabolic points if you want this to be a nice invariant of your relatively hyperbolic structure. There's several different ways to construct this. So if you're interested in it, you should look at Chris Ruska's survey on relatively hyperbolic groups. The other unfortunate fact about this is that there's some kind of difficult to parse topology on it. But sort of the idea is that rays that spend increasingly longer times in Cayley graph distance near its peripheral points. So you can imagine that here's a base point, and I have some ray going out to the boundary, and over here is this is some peripheral stabilized point. There's sort of some well-defined notion of entry and exit. There's some distance here in the Cayley graph between entrance and exit. And the idea being that if you spend increasingly, that distance goes to infinity over a sequence of rays, and that sequence of rays should converge to that peripheral point. So I should say that this kind of construction is due to Bowditch. So basically, you can take this graph with this nice action. In particular, also Bowditch says that gamma is fine, which, if you know what that is, great. If not, don't worry about it. But sort of the point is that this collapsed graph from the one skeleton of your cube complex is kind of a natural witness for the relative hyperbolicity of your group. And so so there is something natural about the relatively geometric action relative to the relative hyperbolicity of the group that you're acting on this cube complex with. And there's a natural way to access the relatively hyperbolic geometry by squashing these stabilized subgraphs to points. And now you have this graph that says a lot of the things you need to know about the relative hyperbolicity of this group. So if you're sort of interested in this, this actually turns out to be very difficult to do all this really carefully. Everything that you think is true, but unfortunately with all this, there's a lot of coarse geometry, and unlike hyperbolic spaces, just sort of coarsely pushing everything forward doesn't quite work exactly the way you think it is, and you need to carefully check everything. So one of the other papers I want to advertise is one with myself and Daniel and Thomas, that's a preprint now on that sort of explains, well, okay, so how do you do this kind of construction where you collapse these points, and gives you natural results about the interactions between relatively geometric cubulations and the Bowditch boundary, which we hope to use in the future as well to construct relatively geometric actions. Okay, so back to the small cancellation free product case. So I told you sort of, well, how you might work on getting to the Bowditch boundary, but we also still need to find these constructed cubulations. So just to kind of scroll up and remind you what our goal was, is we wanted to do this kind of picture here where we take 2 points in the Bowditch boundary of our small cancellation quotient, and we want to find things that are going to separate them. So maybe I should just kind of remind you of the situation. So recall, we had A and B and R, C prime 1,6 set of relators in A and B. So what would you do? First, you want some kind of geometric complex to act on because you're a geometric group theorist. So the idea is to construct a complex using the Bass-Serre tree of A star B and gluing in polygons to get a polygonal complex X. So basically what you're doing is, so say you have each of these relators in the free product, that represents some loxodromic element that takes the base point in your Bass-Serre tree to some other place, and then you're going to glue in polygons along that path so that now these 2 endpoints of that path become identified, and then you need to do everything kind of equivariantly. So if you're interested in kind of how to do this construction properly, you can look in Martin and Steenbock's paper where they actually sort of explicitly build the developable complex of groups and show that its fundamental group is this particular small cancellation quotient. And it turns out that and then its development is going to be some nice polygonal complex. So here's the idea. So now we have, so here's our complex. So we have a polygonal complex X. And imagine that we start with sort of, okay, now what we do is we do the construction above where you can kind of take the one skeleton, collapse, and then take the boundary. You have some sort of notion of the Bowditch boundary from this complex, polygonal complex X. So it turns out that what I said you can do for relatively geometric actions, you can also sort of do for this complex X you get, because it's a similar situation where the stabilizers are controlled. And now what you're going to do is, okay, here's my points X and Y. I'm going to draw a bi-infinite geodesic between them. And now what you want to observe is that this is a polygonal complex, and we're going to cheat because we actually already subdivided this polygonal complex to have even numbers of edges. So you can imagine that if let's just pretend for a second that cells in this complex are hexagons. There's a natural way to build sort of wall-like constructions. So if you've ever built hyperplanes and cube complexes, this is the same idea. Start with the midpoint of an edge. There's a diametrically opposed edge if you have an even number of cells, or sorry, even number of sides in each polygon. Now connect those two. And then in the next cell over, you can do the same thing and connect it up, and you build some kind of natural wall thing. It turns out that with the geometry of this complex, these walls are trees. So we call these are hypergraphs. And hypergraphs are trees. So this is kind of the significance of what this C'(1,6) relation is going to do for you. It's going to allow you to prove that these hypergraphs are really trees. And with this bi-infinite geodesic, what you're going to do is I'm just going to kind of pick an edge here, and then we're just going to take one of these hypergraphs. There's some hypergraph that's dual to this edge. Let's call this Z. And it turns out that what you can do, you can prove that the stabilizer G of Z is full relatively quasi-convex. And you sort of use the geometry to your advantage. Also, I lied a little bit. You have to be a little bit careful. You can't just choose any old edge. It turns out that you have to choose sort of, if you choose this edge, you might worry that this thing comes back and crosses your bi-infinite geodesic, but there's sort of very limited cases where that can do that. And so you find one that's kind of nearby. You might also worry that this wall might sort of come over here and head out to the boundary and pick up your point, but you can also use acylindricity to avoid this problem. So if you're worried about it, that's how you avoid it. Now, the problem with this, so remember we had this A star B and X. This solution works. So this produces enough full relatively quasi-convex subgroups for G, but only with the peripheral structure A and B. So recall that G is A star B mod R. So we get enough full relatively quasi-convex subgroups to get a relative cubulation, but it's going to be relative to the simple relatively hyperbolic structure, just with respect to the factors. If you want to get a relatively quasi-convex, or sorry, if you want to get a relatively geometric action where you have peripheral structures on A and peripheral structure on B, and build a relative cubulation, what you want to do is instead, you want to blow up vertices of X with cubulations for A and B. So the vertex stabilizers of X are going to be conjugates of A and B, and we're going to blow them up with the cubulations that we were given for A and B in the main theorem. So to give you, I won't tell you exactly the sort of detail for how you would do that, but you could imagine that sort of how to blow up. You can imagine starting with the Bass-Serre tree for A and B. So let's just say we take A star B and don't apply any relations. The action on the Bass-Serre tree is not proper and co-compact, but you can kind of turn it into a proper and co-compact action by taking, say, this vertex A, and now I'm going to blow it up into a line. So let's think of A and B just being the integers. I can blow up A into a line, and then I can kind of strategically move these vertices or these edges, which are all labeled by elements of A. I can spread them out now. I can spread them out now so that you end up getting something that's proper and co-compact. And then I'll draw sort of a extension over here, and you sort of blow up B the same way. And now you can imagine how maybe if you do everything right, you'll get a proper and co-compact action on your space by doing this.
So are you adding extra edges? No.
You are adding extra edges.
Okay.
Well, in this case, what I'm really doing is I'm not actually adding. What I'm doing is I'm blowing up where I have the cubulation for A. This is your cubulation for A acting on a line, and your cubulation for B is also acting on a line, right?
Yeah. Okay.
Yeah. So that's kind of the idea, except with you sort of do everything equivalently in the only way you can think of, but this is the only example that I really know how to draw in any even close to meaningful picture.
So in the case you have say the actual A and B co-compact, you have quotient, you have group the group on a point and take universal cover. Is this a correct picture to think?
Sorry, I'm not. So I guess okay. So I should say. So I should say that it's like, yeah, if you do this blow up construction was originally devised by Martin and Steenbock. And if you do this in the situation where you have a proper and co-compact action on your cube complex originally, now you obtain a proper and co-compact action.
Yeah, so is this there's a graph of spaces construction, right? Is it just?
Yeah, in some sense, this is like doing a graph of spaces construction. But then this will get, if you're not in this sort of simplest example where you have like, if you're working with relative cubulations, now these cubulations don't actually carry the fundamental group in some sense. So you'll get, instead you'll get a complex of groups because you have stabilizers. Okay, so I might just say one more thing sort of quickly for sort of the idea. So now the idea is that you have some space. So now you have some space, and I'll call it EG. And there's sort of cubical bits. And there's also polygonal bits. But you can still sort of come up with some notion of what sort of a hyperstructure is what I like to call it looks like. You sort of take hyperplanes and the cubical parts, and then extend through opposite edges like we did before. And this will provide enough. So taking these, the stabilizers of these hypergraph type things, except where they're made out of cubical hyperplanes and opposite edge connections, and taking the walls that you had from down here, you'll actually build a sufficient collection of full relatively quasi-convex subgroups to cubulate your, or to get a relative cubulation of your small cancellation free product. Okay, and I should probably stop there.
Okay, thank you very much, Teddy. Do you guys have any questions?